Series of videos is what I have planned will be on advanced fluid mechanics, and most importantly, I am making these videos just to prepare for my upcoming examination. So these videos I'll be making without referring to any books or notes. Not referring, but without seeing any books or notes. So uh, the lectures will be on advanced fluid mechanics over. The first topic will be Reynolds transport theorem. These lectures will not be having much details or in-depth studies or theories related to the topics, but will be sufficient for examination purpose. So let's say this is a fluid element uh, with a fluid property of alpha. Alpha is a fluid property. This alpha uh, is the fluid property per unit volume, right? This can be anything like density, momentum, energy, anything, right? Now, this fluid element, after let's say a time of delta t, becomes this fluid element. So, this fluid element has a property of alpha t, has a surface area of st, and has a volume of vt. This, after a time t, will have area of s of t plus delta t, a volume of v of t plus delta t, and the property will itself change to alpha t plus delta t, right? Okay, so in Lagrangian frame of reference, the material derivative of alpha shall be, this is, since alpha is the fluid property per unit volume, so we will integrate this over the volume, the entire volume, control volume actually, this one. Material derivative is d of dt. So d of dt, using Fourier transform, we can write it as limit delta t tends to 0, 1 upon delta t, the change between these two, this and this. What's the change? Alpha of t plus delta t minus alpha t this is dv right? So this is from where we start Reynolds transport theorem, right? Okay. So this portion, this entire thing, we can write it as limit delta t tends to 0, 1 upon delta t. Now we will keep the first term same. We will add a new term. This we are doing for a reason. We'll know in some time. Alpha t plus delta t dv, and I'm sorry, this is a minus over here. This minus alpha t dv. Now if we take these two terms, this and this term together, what we will have is integration of delta v this limit can come inside, right? Limit delta t tends to 0, 1 upon delta t alpha t plus delta t minus alpha t dv. This is this part. This is the temporal derivative, right? d alpha dt dv. This is one part. Now if we take this one, we are left out with only these two, right? And this one. These two are right over here. Oh god. This was supposed to be a straight line. Anyways. V of t plus delta t minus this v at the bottom. Alpha t plus delta t dv. These two terms can be clubbed and written like this. So what this actually means? This means this was the original surface at time 1. This surface, let's say I've changed to this, right? So let's say this small segment, right, of surface area ds has moved out with a velocity of v. The normal to this surface has got a unit normal delta n, right? So if we see this, if I can draw it like this is the surface ds. This has expanded like this, right? So this distance, this is in the direction of the normal, so we take a dot product and it has moved, let's say the difference is dt, right? A very small difference. So the volume dv, the infinitesimal small volume increase, can be written as a ds into v dt, right? So if you substitute uh, this over here, what we will get is alpha. Now this v can be changed into s, right? This will be a surface integral now. Alpha ds and we should remember that we had a limit over here, right? So limit t tends to 0, 1 by delta t. This is 1 by dt. So this dt and this dt will cancel. So what we have is this form alpha v n, right, and ds plus the temporal term that we had, d alpha by dt dv, right? This is equal to the total derivative of alpha dv, right? This is a surface integral and these two are volume integrals. So we have to change the surface integral into volume integral. We'll be using Gauss's divergence theorem. So this term will become divergence of alpha v, right? dv. This is the Gauss's divergence theorem. So now the equation becomes d by dt of v alpha dv is equals to v integration of v d alpha from here by dt plus divergence of right. This is the Reynolds transport theorem. The main feature of this transport theorem is the left hand side is the Lagrangian frame of reference and the right hand side is the Eulerian frame of reference, right? This in index notation we can write it as this is the index notation, right? V of dxk alpha uk. This way you can write the index notation. Okay. So we will be using this Reynolds transport theorem to derive continuity equation and the famous Navier-Stokes equation, right? Okay, thank you.